and thank you for the introduction. Metal components, so there might be a mismatch, right? It's polymers on the march, the session we have here, but it's not a mismatch because we need polymers. We need polymers to do our metal components, and I will show this to you in 1 or 2 minutes, where we need polymers. We are a German family group based in southwest of Germany, Pforzheim, founded early 19th century, and we started supplying medical industry already more than 20 years ago. And we are certified also. From applications point of view, we serve for the last 20 years, I would say, quite a large range of medical applications. Current focus is especially on the bottom corner right, surgical robotic. This is really where we have a lot of projects going on. So what do we do? What do we offer? We started 30 years ago with metal injection molding. We extended now a portfolio to additive manufacturing. This is finally our topic today. And I will show to you one of our first mass production project, not in medical industry, but still it is important to show it to you. And also in the last 8 years, we have been developing magnets, MIM magnets. And we are convinced that this is also a very important field for medical industry. So MIM magnets, complex shapes and complex magnetic fields. So we can predefine the magnetic field in the magnet. But let me go to this very fundamental slide. And this is where also I'm going to explain why and where we are using polymer. Our raw material is metal powder. It's always metal powder. And we are combining it with polymer binder. We need the polymer. We are using about 20%. And we need it in order to do the next step and the first production step, which is the shaping. So in MIM for 30 years and now in additive manufacturing also. So where we give a shape to the part. And after this, we already get rid of a polymer. So the polymer is only an enabler for the shaping. The binding, we take out the polymer, and then probably the most important step, the sintering. Sintering where we really achieve the metal part with a density close to 100%. And on the right side, just a few examples of complex metal parts. So what are the benefits of MIM, additive manufacturing, in medical industry and in all industries in general? Most important point, it's about cost reduction. Cost reduction because we achieve the final shape with a minimum material investment and without any machining time. It's extremely helpful also for complicated raw materials like titanium. This is one of one of a very important application. And with MIM, we have a certain design freedom, and in additive manufacturing, we can even go much higher from complexity. I have one example I'll show to you in a few moments. Small dimensions, and for sure, as we can do complex shapes, you see one example. It's not a medical example, but I think it's a very clear one. The yellow part, the machine part, which our customer was doing, and the MIM part, and we could have done it in additive manufacturing. So a strong, very strong weight reduction. But let's go to additive manufacturing. So additive manufacturing, we have 2 processes in-house. I would like to focus today on the mold jet one, because we believe that this is the key process for medical industry. Why do we believe that it's the key one? Because it has a high productivity. Layer thickness also, on the third line item, we can go down to 40 micron. And from process point of view, we have a tray on our booth. The machine is printing first the mold in wax, and then in each layer, the metal paste is printed. So metal paste, just for a reminder, plastic binder and metal particles. Very strong advantages of this machine, of this process. There is a 100% camera control of each layer. and it's the only machine worldwide who is doing this. So each layer is controlled. If there is any issue, the layer is taken out and printed again. And for sure, with a wax, with a metal paste, very important, and we believe it is especially important for medical industry, it's powder-free. It's powder-free, and the post-processing, because the wax is melting, so it's also hand-free. So there is no powder. The parts do not have to be taken out of the powder. With all these benefits, we believe, and we see it more and more, but this is the very competitive metal AM technology. A few examples. On the examples, it's a little frustrating for me. I would like to show much more, but I cannot show the customer projects. So these are a few samples we did internally to show the potential of a machine. You see the size, so up to 10, 15 millimeters. Bone screws, the surface finish is not great because these are bias blanks which are supposed to be reworked. And we believe that this is a great example also, which was done on the machine at our partner location. The Fraunhofer in Dresden has the same machine as we have. We had the first machine in Germany, the Fraunhofer had the second one. And this is one example also of samples of products which can be done, which can be interesting for implants. But let me go, as I mentioned at the beginning, on MoldJet. This is one of the first series applications we have, and I'm extremely happy to show it. It is cosmetic part for the Deutsche Bahn. It's the logo for the first class trains. And very important, it's much, much cheaper than other manufacturing processes. Because we did the part you see here on the left side, we did it at once. And the thread is functional. And for sure, you can imagine that the surface finish had to be good. So with our 120 years of experience, we achieved a very good surface finish. Extremely happy to show this product to you at our booth. And this is, by the way, my last slide. So we are just there. We have medical samples there. I was unwilling to put them on the slides, but please come over just in front of a door.
Thank you. Thank you so much, Bernhardt and Rémy. Yeah, I'm sure there are a lot of questions about this interesting technology, and you know how the game works. You have the Slido app, and you are invited to ask your questions, and we will discuss it later on. Thank you so much again. And we will go on with Dr. Felix Wöhrle. He is coming from DMG, Digital Enterprise SE. He's the head of scientific communications and education. And he's explaining us a case study about 3D printed microfluid devices for cell-based applications. Thank you so much.
Yeah, that's a very complicated title. Basically, I want to talk about a chip that, like the microchip, revolutionized medicine. And the microchip was so successful because it miniaturized technology, and it allowed a much faster progress in the workflow and in the components and collection of data. So DMG is situated in Hamburg, Germany, and I just made sure we have the same origin here with another lecturer here. But DMG has these three main buildings, and in these buildings we have about 400 people working, and about 20% of the workforce is in research and development. So that's a quite huge amount of people doing research. However, we cannot do everything, and this is why we are really happy that we can do research in cooperation with universities. And one such university is the Queensland University of Technology in Brisbane. And this is what I'm going to talk about. This is the part of their research that they did. They focus on microfluidics. And microfluidics, as you know, is this new type of thing where we shrink labs to very small sizes. And since COVID, we've all been acquainted with this. With these devices, we are able to perform very sophisticated chemistry and lab work and avoid lab machinery that we couldn't afford. And it gives us very reliable results. We are happy to have technology like this. Now you can take this up one notch, and we just heard in this lecture about fertilization, how things progress. We are going from cells that is already giving us an enormous advantage to what people would call organs on a chip. So we can have confluent layers of cells working together as the real organ, and we can do experiments on them. And we can get very precise results with this. So this is one study that they talked about. And the interesting thing is really what it says on the bottom here. This enables us to do high-resolution, real-time imaging, in vitro analysis of the biochemical, genetic, and metabolic activities of living cells and functional tissues. And this is really what creates a pathway to treating patients in a very different way. Now, it has been complicated to do that, very complicated. This is a material that has been used to prepare these chips that you do the experiments with. And what you need is not only this very specific material, you need to create it in 2 layers, you need photo chemistry basically to print the channels that you want to have in these structures, and then rinse them out. And this is why you need a clean room. You need this strange yellow light, which is light protection for the photo printing of the circuits in a way that you want to do. Actually, it's really the same as if you would do microcircuits. So wouldn't it be much more favorable if you could use readily available for everyone accessible software, CAD/CAM software, and then design these chips and 3D print them? And we heard about one of the big challenges in the other lecture. They had 6 years to develop a biocompatible resin. And this is why I want to talk about something slightly different, something that can affect us all, about cancer. Can we improve the cancer treatment for patients? And these microfluidic devices are actually one way of doing that. I addressed already one challenge, and it's a big challenge. So there's others. You want to be able to see the cells. You want to do this real-time evaluation of these cells in their environment. And for this, you need a very, very high transparency without distortion, so you can clearly see the cells. Then, and this was probably one of the biggest issues, you need biocompatibility. Actually, you just don't need the cells. You don't want them just to live. You want them to work in a very confluent way, in the exact same way that they do it in the body, so that the results reflect what you are doing to the patient. And for this, we need a bioinert material. And as we heard, 6 years is a long time. And we are very happy that we sort of stumbled across something. We are a medical device manufacturer. We understand the importance of biocompatibility. We place a big impact on this. And for us, it's very, very useful to have this expertise. So we can create these bioinert surfaces. And we heard one other thing, and this is a detection thing. It depends how your experience is with today's high-tech analytical equipment. But very often you have an issue because you want to detect something and that wavelength is blocked. And this is partially true with these resins. We use starter systems that work in a very specific wavelength range, and these can interfere with detection systems. However, and this is the good news, this is where research comes into play, you can overcome this issue. You can find ways or detection systems that detect the products, the molecules that you're focusing on, the reaction that tell you that what is happening in a different range. Now, and this may sound strange, but it is a very difficult situation. What you see here is a cell, one of these microfluidic cells. And you see on the green and black part here the dimensions of this. So top to bottom, maybe 150 microns. That's 1.5 hairs width, or 500 microns, 5 hairs width. That's not much. And when you print, DLP print these systems, then you're printing from a resin. And that resin is entrapped in these volumes that you want to do the reactions in. So one very, very problematic issue can be to get it out. Because these resins, first of all, if they're there, you cannot place something else in, and then they can be toxic for your cells. So you need the right viscosity to suck it out, to clean it out, to wash it out, whatever. And fortunately, that works. I want to show you a little bit about these systems. And one important factor, and we heard that in this lecture before, just prior to ours, that you have to be sure that your printer and your resin work together, because this is crucial for attaining the structures that you want. And this is one such structure, and you can see how small these parts are. This is actually a cell trap where you can collect cells in this and then do the microfluidic things. So this is very, very small. The channel in between is just 80 microns, very small things. But if the resin is correct, and if the environment is correct, cells can survive in these situations. And you can create anything. You can create very sophisticated outlines where the cells live on a layer. You can have solvents or nutrients come from one way. You can have aeration from the top. Anything is possible. But ultimately, you're doing this to improve patient outcome. And if I were a cancer patient, I would rather have a lab check out first which medication and which concentration is working on me, and not be the guinea pig to be tested on, and then maybe if this doesn't work, we go to some other treatment. So the focus will be nowadays to have patient-oriented medicine, and I'm so convinced this will be something to come out. Now, we have to find the right balance between things, and we also have to find the right chemistry. And I'm not just talking about the chemistry in the materials, I'm talking about the chemistry between research partners. And this is why I would like to say a great thank you to the Queensland University of Technology and these people that do a research that we couldn't do, but that would ultimately help patients all over the world to get better treatments. Thank you very much.
Thank you. Thank you, Felix Wöhrle. Nice and a very interesting speech. And may I ask you to have a seat?
Absolutely.
And we will discuss later on about all the questions you have and some other interesting details. And I would like to welcome our last introduction, or speaker of our last introduction speech. It's Dr. Joscha Krieglsteiner. He's co-founder and CPO of Liqtra, and he's going to offer us how we can full use the range of polymers, a new technology for swift processing.
Thank you very much. And also, Mr. Wöhrle, thank you for introducing the company from Hamburg. You have the Moin resin, and I'm coming with a lot of cargo. So yeah, brought some samples. This is Liqtra. Liqtra is a company from Hamburg, as we already learned, and it has a focus on high productivity 3D printing. So we do high productivity printing because we found that there's a need for high productivity. 3D printing takes forever, and we see that in medtech there's some applications that have a strong need for fast processes. One is here. This is a test socket for a leg prosthesis. And if you want to print this in your company, you're going to go for material extrusion. FDM, FFF, you all know it. And you choose it for the advantage that it processes the right materials. You have the technical polymers that you want to work with. It allows you to have it in very small shops even, because it's not expensive compared to other technology. And it is applicable without a lab. You don't need to be in the lab to have a printer running. When it does material extrusion, you can do it even in the office. The challenges you're facing are you need to be experienced. You need to set up a process which can be quite complicated. You have low productivity. A part like this, if you print it in a single nozzle mode, it takes more than 24 hours. So there's a problem. It's not really meeting the needs you have when you have acute cases to serve. And then there's strength. That's common to a lot of layer-wise manufacturing technologies. The strength in build-up direction is lower. It can go down to 60% of what the material is capable of. So here's what we do. We have a technology that uses multiple nozzles at the same time. The Liqtra FX7 is a printer that has 7 nozzles. They can all operate simultaneously. So that is a lot of throughput that is possible. And we have a software that activates the nozzle when they're in the right position to contribute to part buildup. So what we reach, bottom line, is for a part, we're 4 times as productive. And just to make that connection, some of you might have seen this rainbow part. This is what we can do with multiple nozzles. The objective for us is not to print rainbow color parts, but to be productive, more productivity. Multiple nozzles at the same time are more productive. And here's a video. On the left, you see a single nozzle process. And on the right, there's the FX7 printhead. And they both do the same model. They go at the same speed, so the printhead travels at the same speed on both sides. They have the same layer thickness and the same nozzle size. So all the parameters are the same. And the difference you see, because the multi-nozzle printhead is already printing the 3rd model, the difference comes purely from the multi-nozzle aspect of it. So here's a close-up and also slow motion. So you can see that there's no difference in travel speed of the printhead. So none of these measures that you might have guessed are available to speed up a print are taken. The difference comes purely from multiple nozzles. There we are. 1 part on the left, 4 parts on the right. That's productivity. The printer we offer is the FX7 Pro. It comes at quite a huge build space, close build space, of course. 400 millimeters by 300 millimeters approximately, and 0.5 meter in height. And it has a heated print bed. And obviously it has the Liqtra FX7 printhead, what I just showed you. It comes with a software. The software gives you all the slicing, process planning you need to use the printhead. And also the software knows the machine. And that alone takes a lot of complexity out of your job, because you don't have to adjust it. And for those materials that went through a qualification process on our side, you don't even have to know the material. All you have to know is what you want to print. You have to know your parts. And we know machine, software, and material. For a few materials, we went through a process of qualification. And for some, we are in development. So you can expect more materials to be introduced in the future. This is the use case. We're back at the socket. So this now, multi-nozzle mode, prints in 7 hours. So you can expect a medical supply store. They are asked to come to the clinic, do a scan, and they should come back the next day for fitting. That's what the clinic wants, because the patient usually is sent to rehab the next day. When the wound is ready for scan, they're almost gone. And when health insurance, their policy is to pay to that one supply store that does the first treatment exclusively for the first 6 months. So there's a strong interest of the medical supply store to be able to not only scan, but also do the fitting and be the first to work with the health insurance there. So the comparison we have here is made between a Liqtra printer and a number of industrial printers. And one thing you need to notice is that if you have a printer running continuously in production, you will get 4 times as many parts of it. And that's also a cost advantage we're offering. So that's a feature we offer. Having 7 nozzles available, they can be equipped with the same material, but they don't have to be. And this is an example of multi-material. Central nozzle is equipped with a carbon fiber reinforced material, and the rest is equipped with virgin PP. So what's the use of it? You might have different requirements for the structural properties of your part and for the surface properties. And this is not the only way to do it. You can do it the other way around. You can have pure virgin PP on the outside. It comes with controlled surface qualities, and you can have carbon on the inside. An advantage of doing this in multi-nozzle mode is that you don't have to go either material A or material B, but you can process them all at the same time. They extruded simultaneously. And by this, you have both materials meeting when they just leave the printhead. They're at processing temperature, and this way they have a very high tendency to connect, to bond with each other. So if you print with 2 printheads, either A or B, material is going to meet one cold and one hot, and that's a complicated situation to get strong bonding. Then you have more material being deposited in a limited time frame, limited area, limited surface, and that gives you more heat introduction into the part, into what you printed before, lower layers, and that makes them heat up to a higher temperature. This way they are also more active, more with a higher tendency to bond. And what we found, we had specimen measured for PLA, we found an increase in build-up direction of 37%. So, as I said in the beginning, build-up, that's the weak spot of FDM and some other technologies as well. So this has helped quite significantly by going multi-nozzle, 37% up. And for polypropylene, we reach 95% of what the material is capable of. So we're almost isotropic for PP. And all of this comes with the productivity increase. So this is fully compatible. It's not either or, it's both, fast and strong. This is a wrap-up. We talked about productivity, 4 times as fast, multi-material, functional designs. You can make up your minds what you'd like to do, but I think having a surface that meets requirements and something other structural on the inside is quite a good way to go. And their strength. The weak spot in FDM is we tackled it. It's helped a lot.
Thank you. Thank you, Joscha. Maybe we can leave that here and we have a seat.
And take one.
Yeah. And as I see, there are some questions, and I do not see them on the slide. I can please, yeah. There is the first question: why is MoldJet a competitive metal AM technology? I think this belongs to you, that question.
Yeah, clear. Thank you for this question. Main explanation is that we do not have any support structure. You probably all know the metal printing where you need where the laser has a strong energy level.
Yeah.
So you need support structures, which is waste of material, and you have to remove it. So this is certainly the most important point. And second point is that the productivity is quite high. If I take the example of a pin, in one print job, we can do 8,000 pins at once. So these are the two most important points: productivity and no support structures.
Okay. Next questions. What are the challenges in the debinding and sintering step? It's also a question for you. Sintering step for the production of metal parts.
I did not say it, but I guess most of you know it. The shrinkage. During the sintering, the part is shrinking. So this is a challenge, let's be clear. But we're doing it for 30 years with MIM. So now it's more or less the same for additive manufacturing parts. We have equipment, we have a know-how. The design of a part has to be suitable. Yeah? There are design features to be done. But yeah, I said it, it's the most tricky part of our metal parts.
Okay.
Yeah.
I would like to invite you to ask questions too through the Slido app, or more questions. So if you have questions, also when we're discussing, feel free to add more questions. I'd like to go over to Felix Wöhrle, and you pointed out that it's very important to have a cooperation partner. Why is that so important?
It works both ways, because if you have medical device manufacturer like us as a university partner, we know a lot also about registration, about the requirements of the specific authorities that regulate a medical device. And many of the research partners that we're dealing with produce medical devices. So that makes sense to have someone.
So 1 plus 1 is more than 2.
They're very good at their research, but they're bad at registration and the administration part.
I can follow you. Own experience. Yeah. And why are the DMG resins ideal for the workflow of chip development?
Not all of them. This is a very specific example here, but as we've seen, it was originally developed as a splint, so to protect restorations. But it works fantastic, and this is sometimes, accidents happen, and it works fantastic. It has all the properties that I want with very little setbacks and drawbacks.
Yeah.
And this, I think, makes it really interesting for a wider set of things. And when I listen to the lectures that you already had, and especially the other one on the fertilization, I think, there is room for making the world a little bit better.
Yeah. Yeah, thank you. The question was about Liqtra. How do you stop ooze from multi-nozzle?
Reliably. That's as much as I can say.
Yeah.
Of course, it's crucial. If you have nozzles oozing, they're going to destroy the whole surface of the part, and you need a way to prevent them from doing so. And how we do it, I cannot reveal, but we can.
Okay, let's do that. Yeah, and how can material extrusion succeed in competition with a broad range of technologies available?
So in medtech,
not the only one, huh?
By far not the only one. And in medtech, we find that compatibility with skin contact is quite an issue. So we have the resin-based processes. If they are light cured, they are usually not accepted. So there's a distinction from there. And the powder-based ones, they have their place for sure. but they are not affordable for smaller entities. So if you look at the landscape in Germany, medical supply stores, it's thousands, and if they want to work with powder-based processes, they have to go to some centralized approach. They go to print services, or they have in communities where they get machines together, but it's a centralized approach. And having a printer in every place where you have patient care, this is not possible for these technologies. So that's where material extrusion is.
Okay, thank you. And Rémy, what is the initial roughness level of the part after sintering with mold jet?
Very important point. Indeed, I didn't mention it, but the surface finish is a headache. Let's be clear. Mold jet is about RA 5 to 10.
Wow.
Yeah. But again, I would invite to our booth. We have for sure samples with us.
Yeah. A very easy question, Felix, to you. Can anybody buy these resins from DMG?
Yes and no. It depends on the amount that you want to buy and who you are. We would, for example, supply small amounts for research institutions because we want to see how wide the spectrum can be expanded. But for industrial partners, we are not talking about a bottle-by-bottle purchase.
Yeah, okay. So it's very individual. People can talk to you and ask.
Yeah, definitely. My colleague, actually, she's the salesperson here. Could you just stand up so that people can know who you... So any sales questions, that's her domain.
Okay, thank you, yeah. That's what we already had, I think, the process time. Did we talk about process time? Why is process time more crucial for material extrusion than for other technologies? No, we did not talk about that.
I think part of the answer I already mentioned.
Yeah, therefore.
If you have a technology that is able to operate at the point of care, process time is pretty much the only time you have to wait to pass. If you have other technologies that are not fit for being applied locally, they have shipping time. So the process time is not really of a big impact there. Yeah. But for material extrusion, it's at the point of care. Everything you save during the process, you save during the treatment. Yeah. It's just a lot more impact there.
Yeah, thank you. Rémy, I think you must help me with that question. What does it mean, probably, duration printing for Pins Deutsche Bahn?
How much time does it take? So I mentioned it a minute ago, 8,000 parts. In one complete run on the machine, 20 hours. So 20 hours is quite some time, but we speak about 8,000 parts. So,
Wow. That's okay. Joscha, how do you make your technology user-friendly?
I think a lot of the problems that people have in printing comes from the variety of machines and software and materials.
Yeah. Complexity, huh?
It is very complex, and if you combine them freely and your job is to adjust everything, you're probably not going to be successful. So we offer machine plus software, so these two know each other, they're made for each other, and then we have materials that we worked on qualifying to be operating well, to be performing well on the process. So this takes even more complexity out of the equation for the user. And still we're not selling material. It's an open system, but if you go with the materials that we had the qualification on, you don't have anything to do by yourself. You have the machine, the software, and the material, and everything is integrated.
As you told, you just need what you want. You need to know what you want.
Of course, you need to know what you want to print. You're the expert there, and we're the experts in printing. So operating the machine is super easy. We made it step by step, explain on the screen on the machine. So the operator really is there is not much they can do wrong. And then the company needs someone who is responsible, and they can distribute the print jobs to different printers in different locations through the internet. And it's just one person that is in charge for what is printed, how it's printed, and for the process to operate well. That's our job.
So you don't offer the machine, you offer the solution.
We offer a solution,
Yeah.
true.
Okay.
Yeah.
Felix, another question for you. Most cells are from tissues that also need interstitial flow rates, whatever that is.
Yeah,
You have to
yeah.
help me.
No,
And
that's
can the
basically
resin
a
also be
scaffold.
cleaned out from 10 to 50 channels?
Yes. This is experimental. We cannot guarantee for every cell. What we can say is that with the processes that the University of Queensland has developed, they get very good bioinertness, so the cells should grow, and then it's basically limited by the design of your device that you print, but you can print it in one go, and that's the important part. And you also can have these structures, these sort of nets where you can grow the cells, and this is probably what they're referring to. And yes, you need to clean this out as well, which is why the viscosity plays an important role at that moment. If you cannot remove these resins, you don't have your structure available, and you have something else that is probably problematic for the cells to deal with.
Yeah. Thank you. Rémy, which metals can you process with MoldJet?
Portfolio is increasing month by month. Basic, it's 316, 17.4, and titanium, as I mentioned in my presentation.
Yeah, you mentioned that.
Yep.
Okay. And Joscha, is it possible to print TPU, TPE with your solution?
I saw it coming.
Yeah, I saw that you grabbed the...
That's why I have the sample. We see that there is a lot of interest on soft and hard combinations. So soft on the outside, and I think this is where TPU is supposed to be here in that question. Soft on the outside and something more structural, stiffer, stronger on the inside. We have not yet done it, but we are working on it. And having TPU on the outside, if I understood the question correctly, that's something we work on. But we have not yet decided which combination it's going to be, which other material it's going to be combined with.
Yeah, let's add another question. What's the maximum deposition rate of your printhead?
So theoretically, 8 times as much as you can put through a regular printhead, because we have an additional nozzle for support material. But this is theoretical. If we go on large nozzles, 0.8 nozzles, and we have 7 of them, we run into problems of getting the heat away. So these parts, they are printed in with 0.6 millimeter nozzles, and they reach the position rates of almost 100 gram per hour, which is a lot for polypropylene. Also taken into account that polypropylene is very light, low density. This is a lot. I mean, throughput theoretically is much higher, a few hundreds. But the problem there is you need the right part to perform on that level, because the part needs to be huge for the material to have enough time to cool down before you go there the next time. But rates up to 100, that's totally fine on regular parts that we see here.
Yeah, okay. Felix, there's one question for you. Do you 3D print with PDMS or print the mold?
We don't use PDMS. This is old, for us, old technology. We print the mold. And this is acrylic resins, so completely different chemistry that allows for stronger supports, for example, in these situations. But it needs to be very thoroughly and according to a pre-described procedure to be cleaned.
Yeah, yeah. Okay, thank you. And the last question for you, Rémy.
Which one?
When do you recommend MIM versus AM?
MIM needs a mold, gives a better surface quality. We spoke about the roughness. AM, no mold, but more design flexibility. So I believe with both technologies, we are ready to serve all requests.
short question, short answer, and our time is over. Thank you so much here on stage, and thank you all being here, listen to us, asking questions. A big applause to our speakers.